In a previous lecture, we presented the idea of minimal Boolean expressions and the tool of Boolean algebra, which helps us to create minimal Boolean expressions. In this lecture, we're going to present an alternative tool for finding minimal Boolean expressions. That is called the Kmaps, or Kmap. A Kmap is essentially an alternative representation of a truth table that was designed to facilitate the creation of minimal Boolean expressions. The input variables are placed along the vertical and horizontal axes of the map and become the coordinate system for finding corresponding minterms on the Kmap. For example, the top left corner of the Kmap corresponds to minterm 0, which relates to the inputs of A equal to 0 and B equal to 0. Just like a truth table, we can derive a Boolean expression directly from the Kmap. The advantage of the Kmap for optimization is that it creates a visual representation of some of the Boolean identities. For example, if we had a more complex function, we might translate the rows with ones into a Boolean expression. We could then use a series of distribution, complementarity, and identities to derive the minimal solution. This series of identities works because the two minterms differ by only one literal. The Kmap maps corresponding minterms in a way that each cell differs by only one literal from its adjacent cells. So when we see neighboring ones, we will be able to derive the minimal solution directly from the Kmap by checking which literals are the same and which literals are different between adjacent cells. In this case, B' is constant, while A and A' vary. When we expand a Kmap to three variables, we map one variable along the vertical axis and two along the horizontal axis. Notice that the numbers on the columns do not progress from 0 to 3, as you might expect. Rather, the numbers are ordered so that only one literal changes between adjacent cells. This adjacency even wraps around from one side of the Kmap to the other. When we expand a Kmap to four variables, we similarly order the rows so that each cell differs by only one variable from its adjacent cells. We will now explain how to find minimal Boolean expressions with Kmaps. On a Kmap, you want to identify all implicants. An implicant in a Kmap is functionally a group of adjacent ones. These groupings can be 1 by 1 group of cells, 2 by 1 groups of cells, 2 by 2 groups of cells, or any other rectangular grouping where the sides each consist of a power of 2. So we could not have a 3 by 1 group of cells because 3 is not a power of 2. If an implicant is not fully encompassed by another grouping, that implicant is called a prime implicant. This Kmap has 3 prime implicants. We create minimal Boolean expressions by translating the prime implicants into Boolean expressions. For example, all cells in this prime implicant are 1 when B is 1. All cells in this prime implicant are 1 when A is 0 and C is 1. All cells in this prime implicant are 1 when A is 1 and C is 0. Notice that this prime implicant wraps around from one side of the map to the other. To complete the expression, we simply OR these product terms of the prime implicants together. Unfortunately, not all Kmaps are always this simple, and there's not always a unique solution to every Kmap. This Kmap has 2 solutions, and first we'll identify the 5 prime implicants. Some of the cells here are covered by only one prime implicant. These dotted prime implicants are essential because they are the only prime implicants that cover the dotted cells. The remaining other 2 prime implicants are non-essential prime implicants. To construct a minimal expression, we will automatically include our essential prime implicants in the final Boolean expression. Then, we must choose from the non-essential prime lubricants to create an expression that uses a minimum number of product terms. In this case, we can create two minimal expressions that have the same number of product terms. The lower expression has one fewer literals, so it is technically the true minimal expression. But either expression would probably be acceptable in practice.